Okay, I guess we should start. So welcome everybody. Our speaker today is Naber. And in spite of what's written over there, he's going to talk about the relationships between nilpotency and curvature. Okay? Yeah.
Thank you. So I guess I wanted to talk a little bit about it's hopefully going to be a somewhat laid back talk about relationships between curvature and nilpotency. So if you haven't seen all this before, it's kind of fascinating and a little bit surprising. Well, the broad theme is that basically under various curvature assumptions that float around the universe, topology, and what I mean by topology means on what curvature assumptions I'm making, can only really degenerate in a way that's nilpotent in nature. So these nilpotent groups turn out to determine really what the structure of bounded curvature is to a certain degree, and then lower curvature to a lesser degree. So what I'm going to do first is I'm gonna basically remind you of the two main conversations that we're having here. So there's curvature and there's nilpotency. Right. So curvature. I have a Riemannian manifold. My usual spiel at the beginning of my talks. So right, this is a 2 tensor on a manifold that tells you what the length of vectors is, right? It tells you how things bend and twist inside your space. And curvature is a 4 tensor. And by definition, it's the anti-symmetric part of the Hessian vector field. So given 3 vector fields, it gives you a vector field. And if I'm on Euclidean space, then this is 0, right? Doesn't matter if I talk about the x derivative and the y derivative, the y derivative and the x derivative, they're the same thing. I look at the symmetric part, it's 0. If you're on a manifold, this is simply not true. It's not 0, but miraculously, Levi-Civita and Riemann and other guys noticed that this anti-symmetric part here doesn't actually depend on derivatives of z, even though it looks like it does. Right? So this ends up giving you what you call a tensor, right? So it's basically two tensors up from what the metric is. And this is a perfectly fine definition, but it's utterly useless when you're trying to understand what these spaces are and how they behave. And the way you should really think of the Riemann curvature is as being the Hessian of the Riemannian metric. There's the Hessian of the actual Hessian of this guy vanishes by definition of what Hessians are essentially, but this is the right replacement. So in particular, a space with bounded curvature should basically have a Riemannian metric that behaves like a C2 function in Euclidean space, right? And up to diffeomorphism, so that is choosing an actual coordinate chart well. This is true and quite accurate. Note, by the way, that Ricci curvature then becomes the trace of this. Which in 20 words or less explains why Ricci curvature appears everywhere. If this is going to be the Hessian of the metric, then its trace should be the Laplacian of the metric. So Ricci curvature appears everywhere in geometry for the same reason that Laplacians appear everywhere in analysis. Say again?
What is sub A?
Oh, in the orthonormal basis that you pick at a point. So this is a 4 tensor, right? It takes 4 directions and gives you a number. I'm going to take an orthonormal basis at that point. So like you would take the Hessian and then trace it. So you do in 2 directions at the same time and then sum over directions. Plug 2 directions in, sum over them, you get Ricci curvature. And it's like the Laplacian of your metric. Okay. So fine. On the other hand, what's nilpotent? So a nilpotent group is basically almost abelian, right? So it's the closest thing to being abelian that's not, right? The next most complicated thing after having a group operation that commutes, right? So if I were to give a definition, I would say G is nilpotent. If it's lower central series terminates. So that is if I look at G, call that G naught. A sequence of normal subgroups, G1, G2, so forth and so on. Where each GK is the commutator subgroup of G with the previous guy. Right, so it's not abelian, right? So if I take the commutator of 2 things, I don't get 0. Or the identity, as the case may be. But if I take enough commutators, you do, right? So it's not that far away from being abelian. And the example to keep in mind here is the Heisenberg group. It's the one that actually is going to appear in our discussions a lot. So, all right, a basic example here. H3 is a collection of upper triangular matrices. XYZ. Where, let's go ahead and say that X here is inside of R. So diffeomorphically, this guy is like R3. Very good. And there's 1, 2, 3 R's. But if I start looking at commutators of this guy, I don't get 0. But if I take a commutator guy, well, what it basically does is it kills the first term, and then it kills the second. Right. So if I compute these out, I get my H1. It's giving me the collection of matrices, which looks like this, and my H2 will be the subgroup of this guy that's just the identity. So after I take 2 commutators, I get 0. Sorry, if I skip stuff, I mean 0. Note, by the way, a fun subgroup of this that we like, I don't know, on Blackboard, is that if I, instead of letting this be R, if I let it be Z or something like that, we get a nice subgroup, a lattice of this guy. All right, so we can let X, Y, Z is Z instead of R. So, what's the point? So at some point, people ask the question because you just sort of want to. Well, what happens if you have no curvature, right? So coming back to geometry for just a second. So if you have no curvature whatsoever, right, what can happen? We started by saying Euclidean space has no curvature. Does anything else have no curvature? There's basically one reasonable example, which is a torus. Example of 3 torus. So I can take, instead of products of R's, I can take products of S1s, because maybe I'm looking for something compact, because we like compact things in the house. And this is immediately followed by well, instead of asking for 0 curvature, so if it's 0 curvature and it's compact, it's almost that guy. I have to have finite quotients of torus. And that's all that can really happen for 0 curvature. 0 curvature is very, very rigid. If I ask for small curvature instead, what else could I do? So a nice way to visualize this is think of the 3 torus sort of stupidly as being an S1 bundle over the 2 torus. All right, so this guy is sitting inside. So it's the trivial S1 bundle over the 2 torus. If I'm trying to build a space with small curvature, and I don't care about 0 curvature, the game you can play here is that I can look at another S1 bundle over the 2 torus. So I'm going to let N3. So the 2 torus has basically 2 S1 bundles, right? There's the trivial one, and there's the primitive one anyway. So that is, it has a 2 cohomology class, just its volume form here, that has a non-trivial circle bundle over it. So let's build that circle bundle because it's fun. So we have a circle bundle over the 2 torus. So this is kind of like a 3 torus, but it's twisted. It's a twisted 3 torus. And this guy has small curvature, as it turns out. And the reason for this that you can sort of visualize in your head anyway, is well, if I wanted to put a metric on this guy, right, I could take a metric on the 2 torus, that's flat, that's fine. I could pick a connection over this S1 bundle here, pick your favorite, doesn't matter what you pick, right? And then that induces a metric here up to the size of the fiber. So, right, if I know how things kind of are glued together by my connection, and if I have a metric down here, and if I have a size of my fiber, that's a geometry up here. And the idea is that no matter how horrible my connection is on this space, which means that if I'm moving around my 2 torus and my S1 is wrapping around a lot, because I have a lot of holonomy from my circle bundle, even if it wraps around like 1,000 times, if I make the size of this fiber here like 1 over 1 billion, the actual distance it moves by the holonomy is very small. And then that's basically the idea of curvature. So and you can make this all quite rigorous. So if you do this, this guy has small curvature. There's lots of metrics with small curvature. And what does that have to do with that? What that has to do with that is that this N3 here it is actually just my Heisenberg group mod out by my my Z commutative lattice. So just like this is a lattice coming from R3, this is a lattice coming from the Heisenberg group. And
So when you're talking about small curvature, sorry to interrupt you,
Yeah.
you're assuming anyway some other geometric thing. I mean, because otherwise I could kind of dilate things and kind of make it small.
just compact is what I'm supposed to say. So I'll write down a precise theorem in just 1 second, but what I'm thinking is diameter 1, and that's.
Yeah, that's what I wanted to.
Yeah, I'll write that
You
precisely in
have
2 seconds.
Some normalization of the diameter.
That's right. Otherwise, and in fact, you won't even in just 2 minutes, but what you'll mean is I'm going to look at things on the ball of radius 1 or something. You get too big, right? And you can do whatever you want by dilating.
Yeah, exactly.
Okay. So it turns out that this fun example of small curvature, but not zero curvature, it's not the torus. Gromov showed back in the 70s, that's it. This is all that can happen. Right? They must be quotients of Nilpotency groups like this. That's all that can happen. So his theorem was the following. Theorem. So let's let him and G. By the way, I have no time for this lecture whatsoever. I'm just going to stop when I'm out of time. I highly doubt I'm getting nowhere near through everything. Satisfy diameter of M equals 1, just for normalization's sake. Less than or equal to 1's fine. And curvatures are small. So I can take the norm with respect to metric and ask it to be small. Then let's go off. Finite cover. Anyway, so up to finite covers is a no manifold. E.g., one of these guys. And it's a quotient of a Nilpotency group diffeomorphically and almost isometric. You can always whack it to sort of, not preserve it. So it can't be isometric, but it's almost isometric. Nilpotency group by a lattice. So the only way in which you can actually have small curvature is if you're nilpotent.
And every nil manifold can be given such a metric.
Yeah, left invariant one. You can write it down quite explicitly. You can also play this game because actually every nil manifold is circle bundles and circle bundles and circle bundles. Geometrically, I prefer to think that way. So you can play that game too, but you can write down totally explicitly. And I'll point out an extension by Roux that said that this up to finite cover you can say a little bit better. And so you can actually say that it has to be a quotient of a nil manifold by a subgroup by it has to be so-called infranil manifold. So this quotient, it's cover, which is the Nilpotency group by gamma. All right. Gamma is an ennial finite quotient. It has to be a subgroup of lattice and the isomorphisms. And yeah.
The relationship between epsilon and the length of the probability, the degree of probability.
The degree of nilpotency is bounded by the dimension, not epsilon. Right. So it can be at most n basically. Because every single time that you go down, you get another circle. Right. Every time you have a non-trivialness, you got to have another circle on your bundle. So it's at most length n, but it can be in each step. That's reasonable in that length. Roux's observation was basically that, well, you can't whack this metric to make it flat. All right, so if I take this metric here, just because there's a small curvature metric doesn't mean there's a flat metric on it. It'd have to be a torus, but you can whack it to make the connection flat. All right, and so once you do that, you can actually unpeel it. That's really what the statement is here in a sense. So this leads to an interesting thing. So this was done in 78. some 10 years later, Fukaya used this to basically give a complete classification of the local topology of spaces with bounded curvature. So, this is compact, right? I got this diameter one assumption, which, although it's very enlightening, it's maybe sounding kind of restrictive in terms of how you might use this. More broadly, if I just have any space and if it has small curvature, then I can look at the ball of radius 1 and I can diffeomorphically tell you what it looks like, right, from this theorem. And what Fukaya proved. This was 8, which, by the way, requires a really nice point on top of all this. So let's say here. Curvature doesn't matter if I mean sectional or Riemann, it's all the same here. And small. Then there exists an open set. U. So I'm not, so I'm assuming I've got a Riemannian manifold, the curvature is small. I am not assuming diameter 1 here. It's just, it can even just be incomplete. Okay, it can be complete on the ball of radius 2. Is all that you really care. It contains a ball of definite size. Ball of radius 1, which, by the way, you can flip these two, right? Conversely, I can have curvature bounded by 1 and look at a ball of radius epsilon instead, right? So this is every space with bounded curvature. And this ball is diffeomorphic. Not necessarily to an infernal manifold, so one of these guys up here, but to a vector bundle over an infernal. And that's it. So the local topology of all spaces with bounded curvature is sort of characterized by this. So I'll give like 3 examples because that'll probably clarify it a little bit. So dumb examples. So take Rn. I look at the ball of radius 1 around the origin. My open set's just a ball. The infernal here is a point, right? This thing is just a vector bundle over a point. Right. So that's the trivial case, the case where you just have an open chart the way you expect. So basically, when the volume is bounded from below, is how a geometer would say this. You just have to be diffeomorphic to a ball, right? So this is diffeomorphic to a vector bundle over a point. Stupid. Slightly more interesting might be is to take my N3 over there and just cross it by something. Right, so I no longer have diameter 1. And if I look at a neighborhood of some, well, you're viewing this maybe as being a really, really small manifold sitting inside here. And you're not diffeomorphic to Rn-3, but you're diffeomorphic to the trivial vector bundle over Rn-3 if you look at a ball right now. So an entire ball is topologically understood. Pop bundle. So if we look at S3, this is an S1 bundle over S2. And what I can do is I can geometrically squeeze this S1 and make it very, very small. All right, so that gives S3 a geometry which looks almost like S2 when you're staring at it with a fuzzy head. All right, it looks like an S2 geometry. But there's these tiny little circles that are floating around everywhere here. And if I take a neighborhood somewhere around a point, I'm not diffeomorphic to R3. I'm diffeomorphic to S1 cross R3. Ball of radius 1 here is roughly S1 cross R2. I lied. Cross the 2 sphere R2. And another good collection of examples that appears from this quite naturally are like finite volume hyperbolic spaces. All right. So whenever you trail off into the cusps, you always see Nil manifolds appearing. This is not a negative curvature phenomena. This is a bounded curvature phenomena. That is the whole point. You have to get nilpotency there because the curvature is bounded. Okay, so fine. That more or less says everything we can say about spaces with bounded curvature and what their local topology looks like. So topologically speaking, these things are nil manifolds. If you have a bound linear curvature, when you want to weaken this and assume something less. So typically speaking, going from bounded curvature to lower curvature bounds, a lower sectional curvature bound or a lower Ricci curvature bound. You lose full topological control, though typically speaking, you can keep algebraic topology control, depending on what you're talking about. So for lower sectional, the algebraic geometry is still nilpotent in nature, and you can still control it. And I'll make some statements to that effect in just a few minutes. And in the Ricci curvature case, the fundamental group, you can still control in terms of nilpotency. So maybe a good theorem to sort of plop off with, and I can name some conjectures too, because these are fun conjectures. So again, Gromov. So you can't topologically understand spaces with lower sectional curvature, but you can control how badly they degenerate, right? And his theorem, which by the way, I might add, his proof of this almost flat theorem over here had a very lower sectional curvature feel to it. And if you kind of trail through it, there are newer proofs now that don't feel so much that way, but his proof is clearly with lower sectional in mind, and he just made the stronger assumption and got the stronger conclusions out of it.
You're comparing sectional with Ricci, is that what is that comment about?
That comment is about the proof of what I'm about to write down versus the proof of the bounded curvature case over there. They're remarkably similar. This is way more technical, but they're remarkably similar in sort of feel and style to a certain degree. Now that all its bounded curvature, it feels like a lower sectional proof if you do enough of these proofs out there. It's all about triangle comparisons and knowing how things actually, yeah. So what he proved is that if I have a space that has a lower sectional bound, which I can just let be whatever, and a diameter bound, which I can let be whatever, then we don't have topological control, but we can say that the cohomology is not so bad. So the HK of whatever coefficient you feel like are a finite agent that have at most some dimensional constant with all of our constants floating around here, generators.
Can you define sectional curvature for?
Yeah. So if you come over here, sectional curvature of X, Y, it's almost equivalent to Riemann curvature, though it doesn't look it. It's basically looking at certain two plane directions of it, but they recover each other. So it's just about how information is being phrased. This is the Riemann curvature of X, Y, Y, X. So it's certain directions of the Hessian is what it's doing. It's within two planes spanned by X and Y, and you want to look at the part of the curvature coming from that. But it's got all, it's the eigenvalues of this recover the eigenvalues of this. So it's the same information packaged a little bit differently. He made a nice conjecture here, which is still open. Good problem. Sectional is equal to 0. Then the Betty numbers. Are most in choose K. So basically it's torus, and that's the most one kind of expects from this. This is still open. And I would say it's good and open. However, there is a much nicer conjecture out there that actually encompasses this one. You were feeling particularly ambitious and you don't mind wasting a couple of years of your life. So there's a conjecture by Bond, so-called ellipticity conjecture. Although honestly, I've never actually seen him print where he did this originally. Everybody refers to it as the conjecture originally attributed to Bott, and you can go to the 60s and there are papers that say this conjecture is originally attributed to Bott, but no one tells you where to actually find the thing. Let's let it take a manifold with non-negative sectional curvature. Then it's rationally elliptic. And I'll see what that means. Then if I look at the homotopy groups of this, and I tensor them with Q, So I'm getting rid of torsion when I do this. If I look at the rational homotopy groups of our space, it's finite dimensional. The total number is finite dimensional. Yeah. Equivalently and very nicely, that this goes back to work by Dennis Sullivan, which is just outstanding, and a whole bunch of people that followed afterwards. Who's shameful to say, the names are escaping me. That this is equivalent to on saying that the cohomology of loop space grows at most polynomially. So if we look at the cohomology not of M, or the loop space of M, then this is going to grow at most polynomially. And actually, once you know it's polynomial, then it actually has to be most power of n. This implies that actually over there. In terms of non-negative sectional curvature, I would call that the holy grail.
So,
Yeah.
is there some, so can you put up one of these sectional curvature bigger than equal zero metrics on a nil manifold?
No, I don't know if that's been proven. You have to be able to prove that. There's fundamental group restrictions for that. I feel like you have to be able to prove that. Yeah, I would have to cross it. Yeah, no.
That was my second question. So what do we know about pi one in the situation of this conjecture?
And the sixth, okay, so I'll get to pi 120. I'll do that in an orderly fashion. Because that is my next conversation. Okay, so returning to nilpotency. Right, so if we're talking about manifolds and we're talking about curvature bounds, then once we've dropped the two-sided curvature bound, which gave us complete topological understanding of our space, we can still understand fundamental group in the context of lower curvature bounds. So the first theorem along these lines actually was due to Milnor back in '68. And what he proved was that space, non-negative Ricci curvature is all he actually required. Then finitely generated subgroups. The fundamental. Are polynomial. Which instead of telling you what that means precisely, what I'll say is that a few years later, Gromov proved that groups of polynomial growth are almost nilpotent. Right. So if you say plus Gromov, this implies almost nilpotent. This won't interest anybody not in the area, but he didn't even call it Ricci curvature. This paper is so old by the standards of he called it mean curvature, which one can maybe understand causes confusion because there's a lot of mean curvatures in our fields. So at this point is when he sort of made his conjecture, right? That this finitely generated part should be not a necessary assumption.
Since you highlighted before it was sectional, now it's Ricci. Can you say a word? That's when.
Yeah, so I wrote down the condition before. It's like the Laplacian of the
No,
metric.
I know what it means. I'm trying to understand. Can you say why?
Why that?
Why is that? Why is this assuming we can? Right. obviously he's getting that under the weaker assumption. What's the intuition about when you would need sectional and when you Ricci would suffice in either?
Yeah, Ricci controls volume of balls is how one wants to think, like to first order, right? It controls how the volume grows and the fact that when it does or doesn't grow forces other rigidities on your space. Sectional curvature controls all triangles. So that in some sense, if I'm Ricci, it's like the average of all triangles is controlled, but if I'm sectional, all triangles are controlled. Would be kind of the intuition. And for this over here, since this is all about, deck transformations and how things move around, volume is sufficient. And you can use volume to kind of control statements like this. And how the volume grows. That answer your question?
So since you interrupt, can I ask you something? So when you talk about polynomial growth,
Yeah.
would it be easier to prove exponential growth? I mean, is it related? So the difficult part is
The difficult is the polynomial part.
it's polynomial.
Right. Exponential is, I think, basically generic.
Yeah.
And always true.
So it's exactly the polynomial.
Yeah, it's the it pushes it down, right. The nilpotent behavior is sort of what allows for polynomial growth. And in much the same way that the nilpotent behavior allows for bounded curvature, they're not. He actually introduced the notion of Gromov-Hausdorff convergence, this very geometric notion, in the proof of this. Where it's going. The two are not as far apart as it may look on first sight. And actually, what he did do was he did prove this for a lower sectional. All right, so Gromov proved. Actually, he proved it when he proved his almost flat theorem. It was part of it, as I said, it had a sectional curvature field. But he proved sectional curvature is not negative. It's a stronger condition that controls all triangles. And then one has at most C of engineers. Okay, so if we're trying to understand the fundamental group of spaces with lower Ricci bounds or spaces with non-negative sectional curvature, then the next real players in all this was Fukaya and Yamaguchi. So right now the discussion for these guys is just sort of trying to control what they look like. We've actually seen that non-negative Ricci here implies fundamental groups are almost nilpotent. They can't be too wild, right? They have to have this nilpotent behavior. But this proof is highly global in nature. What I'm going to write down is going to feel like a technical refinement of this, not much more, but it's much better than that. So their proof is fundamentally different and generalizes to all kinds of directions, so kind of deserves to be mentioned on its own, even though it sounds like just a technical version of this result. What they proved was a local version of this. They say something called the local fundamental group, which is a fun thing to sort of discuss anyway. So I'll make a remark of it. So the local fundamental group is usually the following. So I'm on a manifold or Riemannian manifold. I can use for an open set, but being a geometer and being on a Riemannian manifold, I'm going to use a ball, but whatever. We call the image of pi 1 of our ball inside of pi 1 of M. A local fundamental group. So what the terminology means, right, is that I'm not gonna look at all loops in my space, right? I'm gonna look at all loops inside some ball maybe, right? But if I'm gonna try to contract them, it's not reasonable to contract them inside the same set you started with. You don't know what this is. Like it could be all kinds of nonsense and wild, right? It's much more reasonable to allow yourself to contract the loops inside of a slightly bigger set, right? Ball of radius 2 or just the whole space itself, right? So I'm looking at all loops inside some fixed sets, hence local. But I can maybe contract them by moving out of that set and doing something else and pulling back in if I want. And my what? Oh yeah. And Yamaguchi proof. Was that if you have a lower sectional bound. No, no. It's almost nilpotent. Slightly lying here. It's almost nilpotent. With some bound number of generators. What they actually proved was almost solvable, and then it was refined by Petrunin, Kapovich, and Tushman to being almost nilpotent. So they proved fundamental group of spaces with lower sectional bounds, again, can't be too wild. It has only so many generators, and they can only basically twist in a nilpotent way. You can't have more complicated types of group structures on the fundamentals of spaces with.
So you're looking at a ball of size 1 and you're looking at a tiny number that you don't.
Kappa is anything you want, right? The number of generators gets bigger as kappa gets very negative, right? But it's anything you want. By the way, they made a conjecture when they proved this. Very nice one. That is also still open.
But I mean, something what you mean by local, it needs to be small. I mean, right, if kappa is very large, then
Not if I allow the number of generators to get bigger, right? It's so the amount of almost will get bigger, but I wasn't specific about how much almost there was anyway. And the number of generators will get bigger. If it's like negative a billion, it'll be a lot more generators than 0. Right? But it'll still be finite and it'll still be almost nilpotent. Did I lie?
confused. I mean, it's just I have a hyperbolic manifold, this is a compact hyperbolic manifold. I mean, pi 1 is not almost nilpotent.
But the image of the fundamental group of the ball radius 1 inside the whole space is the point.
You didn't have -1, right?
Say again?
It's the minus, you have minus K.
Yeah. Yeah, it's just some lower bound, right? If you have a lower bound here, what they prove is the local, so globally speaking, the fundamental group might be much worse, but locally it can only be almost nilpotent up to some level.
Yeah, so locally it would be trivial if you.
Locally, it'll be trivial in that case.
Do you have a lower bound, or an effective lower bound on the almost in the amount?
Yeah, there's an effective lower bound. That actually, they proved almost nilpotent. The effective lower bound was Petrunin, Kapovich, and Tushman. Oh yeah, and then they made a conjecture. Their conjecture was that if sectional is non-negative, then pi 1 of m is almost abelian, not almost nilpotent. This somewhat returns to your question from before. So nilpotent actually shouldn't occur if you have non-negative sectional curvature at all. It should just be purely abelian that appears, and this is still open. It's false for non-negative Ricci, I might add. Under non-negative Ricci, you can produce examples with nilpotent fundamental. Okay, how am I doing? I'm doing fine. Okay, so one more theorem. Then we'll maybe move away. So this question was almost answered. So this conjecture of Milnor about being almost about being finitely generated, Kapovich and Wilking basically use, and this is why I feel the need to write it down, they use almost the same proof as Fukaya-Yamaguchi over there in the lower Ricci case. That proof is so flexible. It actually works under lower Ricci, but you need a lot more structure theory. It took some years to actually develop that. But once the structure theory was developed, you can use basically the same ideas of that proof with some fancy footwork. in order to prove the following. So let's let, satisfy. And I'm gonna say non-negative Ricci. There's a local version, but let's just do the easy, the non-negative case. Then finitely generated subgroups. Of the phenomenal group are almost nilpotent with the uniform bound on the number of generators. So fundamental groups can only come if they're too big, they have to come with nilpotent structure. And that's the only type of group structure that survives. And things like z to the n1 cross ekj to the nj. So too many z factors, too many torsion factors can't occur as fundamental. So what they're saying up here, which is a little bit subtle, is that they're not saying the fundamental group is finitely generated, but they are saying once it's finitely generated, you have at most a fixed number of generators that can ever generate this thing, right? So something a little wonky has to sort of be occurring for it not to be right. And the theorem with Peru and Mola is that there exists some 7 manifolds, non-negative Ricci, whose fundamental group is gamma for any subgroup of the rationals inside the circle, let's say. So let me say that in words. So in particular, take the rationals inside the circle. All right. So think the circle and think of all the rational points. That's group. Then there's a manifold with non-negative Ricci curvature whose fundamental group is the rationals inside the circle. Right? And let's think about that in the context of what we were just saying a minute ago. You know, the rationals have this really neat property where obviously they're infinitely generated. But if I take any finitely generated subgroup of the rationals, it's generated by one guy, right? So you can have more and more generators, but every time you add a new generator, it has to generate the last generators as you're going up. And what they say is that must happen if it's going to occur as fundamental group inside the space. The 2 examples here that are kind of worth considering are just the rationals inside the circle itself, or
Sorry, is 7 the smallest you can do it in?
No, so we did in 6 also. 4 and 5 are open. And I would say there's a host of conditions that are worth actually knowing. Ricci flat's open, but I suspect it's wrong.
Okay,
Taylor's-
I just asked about this.
Yeah, it's okay, but I was gonna say this anyway, so it's an excuse to, right? So whether or not the Milnor conjecture is right for Ricci flat spaces is not known. So if you put that second bound on, our example can have Ricci as small as you want. So actually it seems not inconceivable that it's false for Ricci flat, but this is not proved. It's not known in 4 and 5, and maybe most importantly, and I take this with a grain of salt because this is secondhand information. I'm told Yale thinks it should be true for the Kähler manifolds, and so this is definitely not known one way or the other. So the 2 examples to kind of think about in terms of fundamental group are either the rationals or the dyadic. So these are all rationals whose denominator is some power of 2 going on here. This is the most general guy, and this is because it's a little bit easier to picture everything. When we do it for this guy. I should mention that from a topological perspective, so if you haven't thought about it before, just building a smooth manifold with this as its fundamental group sounds a little wacky. There are known examples of how to do this, right? So the most sort of geometrically popular being the dialectic solenoid complement. But that is not our construction. Our construction is a new construction. I gave a rather painful talk in front of a bunch of topologists just to confirm this. So the way we actually construct this fundamental group does have a slightly different feel to it than past discussions. Okay, all right. I have 4 minutes. That's not very much to me. So maybe in my last 4 minutes, what I'll do is I'll draw a few pictures to sort of get a feel of what something like this might look like. On what the difficulties are, and I doubt I'll get that far in it, but that's okay. So the first point is that so we want to build a space here, right? And we're going to focus on constructing the universal coupling. So I want to sort of draw pictures to sort of see how you might build a space, even just with this fundamental group, forgetting geometry for a minute. And instead of building a space with the fundamental group, I want to build a simply connected space with a certain group action, right? So I want to build a simply connected space with a discrete proper free group action by gamma. Gamma is going to be here my dyadics. The pictures will be a little bit easier to draw. That's one. And just to keep it in the back of our heads, I'm going to let gamma sub k here be the finite group, which is so this is all j, right? And I want to look at the finite subgroups of this guy, which are coming by just looking at fractions whose denominators are 2 to the k or less. So think of this as a circle. And so our gamma naught is this, our gamma 1 is this and this, our gamma 2 is this and this and this. And every time we go up, we double the number of points inside of this. So this is 2 to the minus 3, and 2, 3, 4, 5, 6, 7, 8, yes. And so topologically, I want to build a space, and I'm going to do it maybe to first approximation. We're going to do it by looking at a certain tree. So a diagram tree. So that is, it's going to be a bunch of vertices. It's going to be a bunch of edges. Each vertex is going to represent a certain space. Each directed edge is going to represent a gluing of those spaces into the other spaces that I have written down. And we want to do this in such a way to build the space that we're looking for. All right. So the way this tree should look like is it's going to have an infinite number of vertices. So each vertex is an S3 cross R4. Actually, they're all going to be equipped with certain group actions too, in just a minute. And I'm going to line them up. So horizontally. So our first horizontal line of vertices is just going to be our original group gamma itself. So to a first approximation, our space is the following. For each rational numbers, there's an infinite number of them. Take an S3 cross R4, and we can let gamma act on this by just acting on each copy, right? Obviously, I have a gamma action on this space. Obviously, I have non-negative Ricci curvature. It's highly disconnected. It doesn't count, right? So this is sort of an example, just an infinite number of copies of S3 cross R4 down here, where my gamma action just shifts them around, but it's not connected. My next level of vertices, I'm going to be another infinite number of vertices, which is not going to be gamma. That's going to be gamma mod gamma 1, right? So it has half the number of an infinite number of vertices floating around. And what I'm going to do is I'm going to have hold these. Second minute. These copies of S3 cross R4 are all going to have Z sub 2 actions on them, gamma 1 actions on them. So I'm going to have a global gamma action here, which will shift these guys as before. Up here, the half that survives will still be shifted, but the other half where I glued in will actually just, there'll be a certain Z sub 2 action we'll write down on this guy that'll flip it around. So this guy is still disconnected, but it's half as disconnected as the last guy. Oops. There we go. I was supposed to have half so many vertices. I had just as many vertices.
Ah, okay.
Yeah, exactly.
Okay. It's not one less.
It's not.
Half.
It's half.
Okay.
Thank you. And then I have half as many again. And my next infinite number of vertices would be mod Z to the 4th. And these guys will come up with together. So each time I do this, I have an infinite number of connected components, but half as many each time. And with a group action that's getting bigger and bigger and bigger by gluing together more and more copies of this. What I need from all this are actions so this action here that flipped these two guys now has to survive inside this S3 cross R4. So I've got to figure out what action here is supposed to do that, and so forth and so on. So I glue them up. As it turns out, these gluings are going to be mapping class non-trivial gluings. In the end, like these actions aren't going to be preserved, and I'm out of time, so I'm not going to worry about it. And the interesting part about all of this in the end, as far as Ricci curvature is concerned, is the ability to say on S3 cross S3 that if I look at the standard metric on S3 cross S3, and if I pull it back by a diffeomorphism, even a mapping class non-trivial one, then there is a path of metrics with positive Ricci curvature that connect the two. So somehow there's this very disconnected set of metrics when you let the mapping class group back on it is path connected inside the space of positive Ricci curvature. And this basically lets you geometrically do the gluings that are stuck here. And I'll call that quits. Thank you.
Questions?
Can you repeat that last thing you said? The last sentence?
Yeah, last sentence. There are. S3 cross S3. Do with standard metric. You need diffeomorphism. If actually an equal variant version was necessary or whatever. Then there exists a family of metrics U sub P. And strictly positive Ricci on S3 cross S3 such that G naught is G naught, the standard metric on a 3 sphere. And V1 is the pullback of the standard metric by this diffeomorphism. If this diffeomorphism is mapping class trivial, this is dumb. All I have to do is find a family of diffeomorphisms that go from one to the other. And they're all geometrically the same. When this is mapping class non-trivial, these guys are highly non-trivial, the G sub T's. They squish and do all kinds of nastiness. In fact, they're not completely explicit. But you can exist.
You can't do it with sectional control, right?
Absolutely not. No. Yeah.
So it's got something to do with volume. I mean, that's the question I was asking you. What's the intuition about in high dimensions when you have make constructions which are different when you have Ricci?
Right. So when you're doing a twisting along here, what's going to happen is that you're going to squish certain directions in order to compensate for too much movement in another direction. The fact that like Laplacian is an average of Hessians mean that I can have a very negative as long as I have a very positive in another direction, right? And so the high dimensions gives me something to squish when you're moving around.
So the 7-dimensional restriction comes because of this S3 cross S3.
We have down to dimension 6, but it's much less pictorial. It's basically the same idea, but it's just it's less pretty looking.
So what blocks you from going down?
The ability to squish. Now, once you get to dimension 4, I actually imagine that there's a counterexample. It's Ricci flat. Like building Ricci flat is about the same difficulty as building non-negative Ricci at that point, because you can't squish stuff. You can solve stuff. You can't squish stuff. It's S1 bundles, not S3 bundles or S2 bundles.
Yeah, sorry. Just waiting.
Does this kind of result have interest in some? Finding.
Well, for Ricci people, I'll let you build more weird examples. So if you do something like this, so I don't think we bothered to write it up because you can build these by other methods, but by a single gluing, you can basically build positive Ricci metrics, for instance, on all exotic spheres and things like this. Right? It lets you do mapping class non-trivial kind of weirdnesses that float around. Past that, I don't know. Past the ability just to make wonky examples that tell you other theorems aren't true. I don't know.
Yes.
The theorem of Milnor also gives an upper bound, right, of polynomial degree.
Yeah,
And
yes.
if you take a countable group satisfying the assumptions in his theorem, so every finitely generated subgroup of Gromov at most n to the d,
Yeah.
can it be imagined that maybe all such groups can be?
So I would be nervous about making a statement about group theory. I would say that probably, at least in this context, the ones that arise from here, I would imagine that the general version of this is that your fundamental group should be a finite extension of a countable subgroup of a nilpotent Lie group, something like that. Like you might imagine, so here it's like you got S1 and your countable dense rationals. You might imagine other rationals inside of other nilpotent Lie groups. Those might be fundamental groups, and finite extensions of those might work. But something like that might be the extent to what you're talking about.
But there are no, because in principle, Milnor's assumption is a bit less than you're saying, right? But then, so there are no other obstacles a priori offered.
No, not a priori, right? So basically that bounds the dimension of the nilpotent group that you have to work with. You just got to make sure they all go in the same one, and you basically have it. It may actually be just a few lines. I haven't thought about it.
Again, about the same statement. Do you know if somebody studied this before? I mean, the mapping class group acting on.
No, so guys like Wraith and his cohorts, they do a lot of these gluing constructions with plumbing techniques, but it's always trivial gluings, but lots and lots of them, right? So you can recover an exotic sphere.
Mapping
you know.
class in general.
No, not in the context of Ricci anyway. I mean, there's lots of stuff on mapping class groups.
Sure.
But not in the context of understanding the geometry. Yeah, no.
Ricci.
Not that I'm aware of. Yeah, no.
Do you think that?
There are better theorems to be proved, if that's the question, yes.
Okay, there seem to be any more questions, so thank you.